Now this section is about radicals. We encounter radical numbers pretty easily, like when you were dealing with triangles, for instance, right triangles. So let's see if you've got a triangle, right triangle. One side's 8, one side's 4, and you want to find the other side here. Let's call it C. Well, everyone knows the Pythagorean Theorem. And it says that the hypotenuse square is the sum of the square of the lengths of the legs of the triangle. So C squared is A squared plus B squared. So in this case, if I want to find C, I know that C squared is going to be 8 squared plus 4 squared, which is what? This is 64 plus 16, that's 80. So C would be the square root of 80. Okay? And often we want to simplify our square roots. So this video is mostly about how to simplify or rewrite square roots. Okay? And our basic tool is we're going to use the fact that the square root of a times b, that's exactly the same as square root of a times square root of b. To convince yourself, you could just square both sides and you could see that both sides would be equal to AB. Okay, and what kind of A and B are we going to choose? We're going to use that little rule if we can find A or B that are perfect squares. So I'll show you what I mean here using square root of 80. Now if in square root of 80 I can, there's a perfect square that divides evenly into 80, I can use the previous trick. Now 80 is, I know it's 16 times 4 because I know numbers pretty well, and 16 is a perfect square. So I can write this as square root of 16 times square root of 5. Now 5 is not a perfect square, but 16 is, so this is 4 root 5. And there are no other perfect squares that divide evenly into 5, so I'm kind of done here. So now maybe you'll tell me, well, I didn't know that 16 was going to fit into 80. Well, that's okay. You could also have said, well, I know that 4 fits into 80, and 4 is a perfect square. So you can do that. 80 is 4 times 20. So you can use the rule. This is root of 4 times root of 20, and 4 is 2. But then, after that, you have to ask yourself the remaining number I have here, 20. Can I also divide that even into another, by another perfect square? And then the answer is yes. You can still keep on dividing by 4, 20, so you can apply it a second time. And then you get 2 root 4 root 5, and root 4 is 2. So 2 times 2, 4, and then you end up with what I had previously. So it's just that if you're able to get the largest perfect square that fits into your number, you're going to save a few steps. Okay, but if you don't notice it, it's okay. You can just keep on going. So maybe another example, if you've got root of 32, a to the 5, b4, okay. Once again, we're trying to see, well, are there perfect squares that are factors of this expression? Well, 32, that's 16 times 2. Well, 16 again. So that's good. I'll write 2 times 16. A is a to the 5. Well, or maybe let's start with b. B to the 4. B to the 4 is always, if it's an even power, it's always the square of something, right? It's because using our power rule, 4 can be written as 2 times something because it's even. So b to the square squared, okay, is b to the 4. As for a to the 5, actually I'm going to run out of space here. A to the 5, 5 is not even, but in a to the 5 hides a to the 4. So I can write a to the 5 as a to the 4 times a. And a to the 4, I can, since it's even, I can think of it in terms of a squared squared. So I've got b squared squared, a squared squared. Okay, so overall I can write root of 16, a squared squared when well, I'm going to square root that, a squared squared. I'm going to the b squared is also going to be square rooted, and finally I'll just be left with root of 2a, and 2 and a are not perfect squares. So this is going to be 4a squared b squared root of 2a. So obviously this step can be skipped once you get comfortable with everything. This step too, actually, okay, in some way, okay. And after that, there are other things we do with rational numbers besides simplifying them. Sometimes we want to rationalize them. So rationalize the denominator. So imagine you've got this, or you've done some computation and you end up with this after simplifying. Can we simplify root of 10 furthermore? No, we can't. There's no perfect square that fits into 10. But let's say we don't want to have a radical in the denominator. Sometimes this is something we want to do. I want to remove the root of 10 from the denominator. So how do I do this? Well, one trick is to notice that if I multiply root of 10 by itself, it's going to become 10. There won't be any radical. But if I do this, I need to do the exact same thing in the numerator as well, because otherwise things are not going to be equal. So if I multiply and divide by root of 10, I'm essentially multiplying by 1, right? So I haven't changed anything. But what's cool now is that root of 10 times root 10, that's just 10, right? So I've removed the radical in the denominator. That's called rationalizing the denominator. And in the numerator, this becomes 2. Root of 3 times root 10, I can write that as root of 30. And try to ask myself, maybe I can simplify root of 30 after that. So overall, this is what this is 30 at the bottom. 2 over 30 is 15. 1 over 15. So this is root of 30 over 15. And in 30, you can, if you think about it, there are no perfect squares that divide evenly into 30. So we just leave it like that. So that's one way. What if I have a sum with a radical in the denominator? Now, it's pretty easy to convince yourself if I multiply by 1 plus root 5 above and below, I'm not going to change the expression, but I'm not going to rationalize the denominator. By multiplying these two together, I'm going to end up with something like this. So moral of the story, I'm going to be stuck with still a square root. So that's not the way to go here. But if I change the plus to a minus, it's going to work. Why is that going to work now? It's because we're using the following trick. If I have a plus b, then I multiply by a minus b, it's going to give me a squared minus b squared. So if either a or b has a radical, or is a radical, it's going to be squared. So, it's going to go away. So let's take a look here. At the top, I've got 2 minus root 5. 2 times 1 minus root 5. At the bottom, I'm going to get a squared, so 1 squared, minus b, which is root of 5, squared. Now, root of 5 squared is going to be 5. So this is going to be 2 minus root 5, 2 times 1 minus root 5, sorry again. 1 minus 5, and 1 minus 5 is minus 4. And 2 over minus 4 is minus a half. So this is going to be minus 1 minus root 5 over 2. I can distribute the minus sign, and if I do this, I get this, and then change the order of the addition to make it look nicer. So this is just to make things look nicer. But in terms of rationalizing my denominator, this accomplishes the task, but this just makes it look a bit nicer. So if we stop here, this is completely okay. But if you see that in the answers, okay, just know that you can manipulate the answer a little bit to change the way the answer is written. We can also rationalize numerators. Okay, so this is actually taken from almost the first week of calculus, maybe second week. Rationalize the numerator. So I want to remove the radical in the numerator. Okay. So I say it's taken from calculus because this is linked to a task that we want to accomplish in calculus. Okay. So how do I remove the radical from the numerator? I'm going to use the same trick as here. Okay. So if I multiply root of x minus 1 by, and this is called the conjugate, by the way, you take the same expression, but you change the sign in between the two terms. So if it's a minus sign, you change it to a plus. Before the previous example, it was a minus, we change it to a plus. With a plus, we change it to a minus. Now it's a minus, we change it to a plus. So if I multiply by this, I'm going to be multiplying a minus b times a plus b. So in the end, I'm going to get a squared minus b squared, and there won't be any square roots at the top. Okay? But of course, if I do this, it's going to introduce a radical in the denominator now. Okay, we keep things factored because we're hoping that maybe things will simplify in the end. And you see in this example, I've got x minus 1 and x minus 1 that are common at the top and at the bottom. Okay, and I can sort of remove them. Why can I do this? It's because this is the same as x minus 1 over x minus 1 times 1 over root x plus 1. Okay, now this is 1. So multiplying by 1 doesn't change anything. So that's why I can sort of cross them out, and I'm left with 1 over root x plus 1.